Hello, welcome back to Control Systems Lectures. In the last lecture, we showed how to design control systems to meet both stability and steady-state error. However, I stated that meeting these requirements does not imply that the desired transient characteristics are fulfilled. In this lecture, we will introduce the root locus method, which will eventually enable us to design a second and higher order control systems to meet all three design specifications, which are the transient characteristic, stability, and the steady-state error. Therefore, by the end of this lecture, you will be able to do the following. 1. Define a root locus. 2. Sketch the root locus of control systems manually and using Matlab and be able to interpret the results. 3. Evaluate the root locus for determining the poles of a closed-loop system. 4. Use the root locus to determine the system stability and transient behavior as a system parameter is varied for second order and higher order systems. The root locus is a graphical technique that gives us a qualitative description of a control system's performance. It is also a quantitative tool that gives more information than the previous methods we have discussed. So far, the gain and other system parameters have been used to design systems to yield desired transient response for first and second order systems. The root locus provides us with more capabilities to design for first, second, and higher order systems. Before we present the root locus, let us review two important concepts that we need for the discussion ahead. These are the control system problem, and second, complex numbers and their representation as vectors. Let us start with the main issues of control systems. Using the feedback control system in this figure and expressing our g of s as n subscript g of s over d subscript g of s and h of s equals to n subscript h of s and over d subscript h of s, where n and d are factored polynomials of the numerator and denominator. Therefore, our open loop transfer function will be given by k n subscript g n subscript h over d subscript g d subscript h, where k is the gain and n subscript g n subscript h are the numerators of the g and h respectively, and d subscript g d subscript h are the denominators. It is obvious that the poles can be easily found, as these will be the poles of the feed-forward and the feedback elements. Secondly, changes in k will not affect the open loop poles. On the other hand, the closed loop transfer function is given by t of s, which is equals to k n subscript g d subscript h over d subscript g d subscript h plus k n subscript g n subscript h. It is clear that we cannot determine the poles of t of s unless we factor the denominator. Let me illustrate this. Consider a system whose g of s is given as s plus 1 over s plus 2, and h of s is given as s plus 3 over s plus 4. The open loop transfer function will be given as g of s h of s, which is k s plus 1 s plus 3 over s plus 2 s plus 4. We can see that the poles are easily known to be 0, minus 2, and minus 4. On the other hand, the closed loop transfer function will be given as k s plus 1 s plus 4 over s cubed plus 6 plus ks squared plus 8 plus 4ks plus 3k. It is immediately obvious that the poles are not easily known, and secondly, the t of s will change with change in k. Since the system's transient response and stability depends on the poles of t of s, we can only know the system's performance if we are able to factor the denominator for specific values of k. This is where the root locus strength lies. The root locus is able to give us a clear picture of the poles of T of S as K varies. The second concept required for the understanding of the root locus method is the complex numbers and their representation as vectors. Any complex number, sigma plus j omega, can be graphically represented as a vector as shown in this Cartesian coordinate form in this figure. The complex number can also be described in polar form with the magnitude m and angular theta. If a complex number is substituted into a complex function f of s, another complex number will result. For example, if a complex function is given as f of s is equals to s plus a, substituting for the complex number s equals to sigma plus j omega yields f of s to be equals to sigma plus a plus j omega, which is another complex number. This number is shown in this figure. Note that f of s has a 0 at minus a. If we translate the vector a units to the left as shown in this figure, we have an alternative representation of the complex number that originates at the 0 of f of s and terminates on the point s equals to sigma plus j omega. We can therefore conclude that s plus a is a complex number and can be represented by a vector drawn from the 0 of the function to the point s. For example, the complex number s plus 7 as s tends to 5 plus j2 is a complex number drawn from the minus 7 to the point s, which is 5 plus j2 as shown in this figure. We will now apply this concept to a complicated function. Assume a function given by equation 8.1 where the symbol capital Pi means the product. M is equals to the number of zeros and n is the number of poles. Note that each complex factor s plus z and s plus p can be represented as a vector. The magnitude m of f of s at any point, say s, is given by the equation 8.2, where the length of a 0, s plus z with the bars in between meaning the length, is the magnitude of the vector drawn from the 0 of f of s at minus z subscript I to the point s. Similarly, the length of a pole, s plus p subscript j, is the magnitude of the vector drawn from the pole of f of s at minus p subscript j to the point s. Then the angle theta of f of s at any point s is given by equation 8.3, where an angle subtended by a 0 is measured from the positive extension of the real axis of a vector drawn from the 0 of f of s at minus z subscript I to the point s. Similarly, an angle subtended by a pole is measured from the positive extension of the real axis of a vector drawn from the pole of f of s at minus p subscript j to the point s. We will now use an example to demonstrate this concept. Given the function f of s is equals to s plus 1 over s plus 2, find the function f of s at the point s equals to minus 3 plus j4. To solve this problem, we need to find both the magnitude and angle of this function from the complex number. This problem is graphically represented in this figure. We draw each vector to terminate on the selected point s equals to minus 3 plus j4. The vector originating at the 0 at minus 1 has a magnitude of square root 20 and an angle of 116.6 degrees. And the vector originating at the pole at the origin is 5 magnitude and angle 126.9 degrees. The vector originating at the pole minus 2 is square root 17 magnitude and an angle of 104 degrees. Substituting these into equation 8.2 and 8.3 will yield our result as the magnitude being 0.217 and the angle minus 114.3 degrees. Please complete the skill assessment exercise 8.1, which is in page 391 of your textbook. Hello, welcome back to Control Systems Lectures. In the last lecture, we presented two essential concepts that will enable us to understand the rest of the materials in our study of root locus. We explained the main problem with the feedback control system, in which the poles of the closed-loop transfer function are not easily known without factoring them, and which are also influenced by the gain of the system. Since the system's transient response and stability depend on the poles of T of S, that is the closed-loop transfer function, we can only know the system's performance if we can factor the denominator for specific values of K. Secondly, we reviewed complex numbers and their vector representation. We are now ready to define root locus and apply it. Let us use the first order system to define and explain the root locus. Consider the first order feedback control system shown in this figure. The open loop transfer function will be given as K over tau S, and the closed loop transfer function is K over tau S plus K, where K is the gain of the system and tau is the time constant. The root locus is plotted by varying the value of K from 0 to infinity. It will start from the open loop pole, and if there is an open loop 0, it will terminate at that point. Otherwise, it will terminate at infinity. In this case, the root locus will therefore start at s equals to 0 and terminate at infinity. To trace the root locus, let us take tau equals to 5, and then we vary the value of k of the characteristic equation 5s plus k equals to 0, and finding the poles, which we will then plot on the s-plane, where s is equals to minus k over 5. We can see that the root locus started at s equals to 0 and moves along the real axis to infinity. Since this is a first order system, we have one locus. The second order control systems are equally straightforward. Let us draw the root locus of the second order system shown in this figure. The open loop transfer function of the system is given by g of s of s, which is k over s plus 10. Therefore, the open loop poles are s equals to 0 and s equals to minus 10. And the open loop 0 do not exist. Therefore, the two loci will start at s equals to 0 and s equals to minus 10. And both loci will terminate at infinity. The closed loop transfer function is k over s plus 10 plus k. And the characteristic equation is therefore s squared plus 10s plus k equals to 0. You can immediately see that the poles depend on the values of k. To plot the root loci, we will vary k from 0 to 50. This could be to infinity. And for each k value, we will compute the closed loop poles, which are then tabulated in this table. The root loci will start at the open loop poles s equals to minus 10 and s equals to 0. Hence, with k equals to 0 for the closed loop transfer function, the roots are on the starting points, that is minus 10 and 0. And as k varies, the poles of the closed loop indicates the locus from 0 moving to the left of the real axis, and the locus from minus 10 moves to the right on the real axis. This is better visualized from the root locus plot itself. The root locus shows the changes in the transient response. As k varies, the poles are real and distinct for gains less than 25. Therefore, for this range of k values, the system is overdamped. At k equals to 25, we have repeated roots, which means our damping ratio is 1, and hence our system is critically damped. The system then breaks into the complex conjugate region for gains above 25, and hence the system becomes underdamped. Now, if you focus on the underdamped region, you will observe that regardless of the values of the gain, the real part of the complex conjugate remains the same. Since the settling time is inversely proportional to the real part, it means that for the second order system, the settling time will remain the same for gains above 25. Also, as we increase the gain, the damping ratio decreases and hence our percentage overshoot increases. Since the damp natural frequency is equal to the imaginary part of the pole, as the gain increases, there will be a reduction of the peak time. And finally, since the root locus never crosses into the right side of the S-plane, it means that the system is stable and will remain stable for all values of the gain. So now, so far, we have used examples of first order and second order systems to show how the root locus is plotted and to provide some insight into the information that will enable us to use it for both analysis and design of control systems. In both cases, we needed the factorized form of the denominator of the closed-loop transfer function to plot the root locus for various gains. For systems of higher gains, say 5th or 10th order, this will be near impossible. Now, I would like to provide a more general procedure for plotting the root locus for higher order systems. First, we will explore the properties of the root locus that will enable us to sketch the root locus for higher order systems without having to factor the denominator of the closed-loop transfer function. Let us consider this general control system. The closed-loop transfer function will be given by equation 8.4. A pole S will exist when the characteristic polynomial in the denominator becomes 0, or k g of s h of s is equals to -1, where -1 is represented in polar form as the magnitude 1 and the angle 2k plus 1 multiplied by 180 degrees, where k is a whole number, 0 plus or minus 1 plus or minus 2, and so on and so forth. Alternatively, a value of s is a closed loop pole if the length of the vector kg of sh of s is equals to 1, and the angle kg of sh of s is equals to 2k plus 1 multiplied by 180 degrees. Equation 8.5 implies that if a value of s is substituted into the function kg of sh of s, a complex number results. If the angle of the complex number is an odd multiple of 180 degrees, that value of s is a system pole for some particular value of k. And since the angle condition is satisfied, we need to satisfy the magnitude criterion. That is equation 8.6. Therefore, k is equals to 1 over the length of g of s, h of s. What we have just discovered is that a pole of the closed loop system causes the angle of kg of sh of s to be an odd multiple of 180 degrees. Also, the magnitude of the open loop transfer function must be 1, implying that the value of k is the reciprocal of the magnitude of the open loop transfer function when the pole value is substituted for s. Let us demonstrate this with the previous second order system, in which we had closed loop poles at -9.47 and -0.53 when the gain is 5. For this system, therefore, kg of s, h of s is equals to, that is the open loop transfer function, is equals to k over s plus 10. Substituting the poles at minus 9.47 for S and 5 for K yields minus 1. You can try solving for the other values of poles and their corresponding gains to confirm that you will always get open loop transfer function multiplied by the gain equals to minus 1. The angle condition, equation 8.5, is better visualized graphically. Let us apply the complex number concept we reviewed in the last lecture to the root locus of this block diagram. You can see that the open loop transfer function of this system is given by equation 8.9, and the closed loop transfer function T of S is given by equation 8.10. If point S is a closed loop system pole for some value of gain K, then S must fulfill the condition of equation 8.6 and 8.7. These are the magnitude condition and the angle condition, respectively. Let us consider a point S equals to minus 2 plus J3. The angle condition will be given as the sum of the angles of the zeros represented by theta subscript 1 and theta subscript 2 minus the angles of the poles given by theta subscript 3 and theta subscript 4. This gives us a sum of 70.55 degrees, which does not satisfy the angle condition. Therefore, the point minus 2 plus J3 is not a closed loop pole for any gain. If we repeat the same calculations for a pole S equals to minus 2 plus J square root of 2 over 2, the angle will add up to 180 degrees, which means this point is on the root locus for some value of gain K. We can then calculate that value of gain using equation 8.11, which will yield K is equals to L subscript 3, L subscript 4 over L subscript 1 and L subscript 2. So if you have to compute the length of these vectors, and this will give us 0.33. This means that the point S minus 2 plus J square root of 2 over 2 is a point on the locus with a gain of 0.33. Let us solve an example. Given a unity feedback system that has the forward transfer function g of s equals to k s plus 2 over s squared plus 4s plus 13, do the following. A. Calculate the angle of g of s at the point minus 3 plus j0 by finding the algebraic sum of angles of the vectors drawn from the zeros and poles of g of s to the given point. B. Determine if the point specified in A is on the root locus. And C. If the point specified in A is on the root locus, find the gain K using the length of the vectors. The open loop transfer function is given as g of s h of s, which is equals to k over ks plus 2 over s squared plus 4s plus 13. Therefore, we have 1, 0 at minus 2 and 2 poles at minus 2 plus or minus j3. We can then draw the vectors as shown in this figure. And from the vectors, we check for the angle conditions, which is the sum of angles is equals to 180 degrees minus tan inverse minus 3 over minus 1 multiplied by tan inverse minus 3 over 1, which comes down to 180 degrees. Hence, the angle conditions are met. Now let's look at B. Since the angle conditions are met, it means the point minus 3 lies on the root locus. We can now find the gain value for this point, which gives us k is equals to 10. Please go through the example again to consolidate the concepts. Hello, welcome back to Control Systems Lectures. So far, we have shown how two essential conditions must be fulfilled by a point S to lie on the root locus. These are the angle criterion and the magnitude condition. In this lecture, we will now provide some rules that will enable us to sketch the root locus that will give us an intuitive insight into the behavior of a control system. First, let us review the properties we have already discussed. The angle condition, represented by equation 8.12, which is the same as equation 8.7, indicates that given the poles and zeros of the open loop transfer function, a point in the S-plane is on the root locus for a particular value of gain k, if the angles of the zeros minus the angles of the poles, all drawn to the selected point on the S-plane, add up to 2k plus 1 multiplied by 180 degrees. The gain k at this point that has fulfilled the angle criterion is found by dividing the product of the pole length by the product of the zeros length, as given by equation 8.13, also represented by equation 8.11. Let us now give some general rules for plotting the root locus. The first is the number of branches of the root locus. Recall the example of the second order control system in lecture 802. I have reproduced it here. You can observe that there are two branches, the blue branch and the green branch. A branch is defined as the path that one pole traverses, which means that there will be one branch for each closed loop pole. The first rule, therefore, is the number of branches of the root locus equals the number of the closed loop poles. In other words, the order of the characteristic equation yields the number of branches of the locus. Like we have seen that the second order system yielded 2 branches and the first order system had 1 branch. The next rule is that the root locus is symmetrical about the real axis. Again, if you consider the second order control system example, you will see that the rule is obeyed. The next rule is the real axis segment rule. This rule states on the real axis, for k greater than 0, the root locus exists to the left of odd number of real axis finite open loop poles and or finite open loop zeros. The fourth rule provides the starting and the ending point of the root locus. The root locus begins at finite and infinite poles and ends at the finite or infinite zeros of the open loop transfer function of the system. For example, for this system, the open loop transfer function is k over s plus 10. This means that the path of the root locus will begin at s equals to 0 and s equals to minus 10. And since there is no zeros, which would have been finite ending point, the two loci will terminate at infinity, just as the root locus plot indicates. The last rule requires a little more explanation. The behavior of loci at infinity and the determination of the asymptotes as the poles approach infinity is determined from the following fact. The angle of the point s minus p subscript I and s minus z subscript I becomes approximately the angle of s. Therefore, the angle criterion becomes equation 8.15, and this will yield equation 8.16. The angles of the asymptotes that guide the direction of the root locus are therefore determined by equation 8.17, and the number of distinct asymptotes is given by n minus m, that is the number of poles minus the number of zeros. We can also determine where the asymptotes intersect the real axis. This is given by equation 8.18, which is simplified to equation 8.19. And finally, we also need to find out when the root locus breaks away from the real axis and where it breaks in again. Along the real axis, S is equals to sigma minus J0. Therefore, to find the maximum and minimum values of the gain K will correspond to the breakaway and break-in points respectively. Hence, equation 8.20 will be used. These rules will be used in an example to demonstrate their application. Let us summarize the rules for sketching the root locus for a higher order control system. 1. Number of loci is equals to the order of the characteristic polynomial. 2. Symmetry. The root locus is always symmetrical about the real axis. And 3. Real axis segment. For k greater than 0 along the real axis, a root locus exists to the left of an odd number of real axis finite open loop poles and or finite open loop zeros. And point 4, starting and ending points of the loci. Each locus starts at an pole and terminates at a 0. Note that the poles are indicated by X and the zeros are indicated by 0. However, there are usually more X than O's, therefore the remaining loci will terminate along asymptotes at infinity. Point 5. Determine the asymptotes as the poles approaches infinity. And 6. Determine the breakaway and break-in points of the loci along the real axis. I will use this illustrative example to explain the rules during our contact session. Thank you for listening.